Hello, everyone, and welcome to Bird Process Equipment's educational webinar on pH system design. I'm Mark Turgenti, the Director of Design Engineering, and I want to welcome everyone here today to this broadcast. Today we're going to talk about a number of different aspects related to pH system design, including some fundamentals about the nature of pH and waste in general. We're going to look at some of the different types of systems which are available between flow-through, batch, and as well as hybrid style systems. Take an in-depth look into some of the various componentry that goes into the systems. We'll review quite a bit about how to actually design these systems, both in terms of flow as well as the nature of the waste. And then we'll go through a couple of case studies on sizing, talk about a few standard designs which are available, and then we're going to kind of end off with a few different system examples. We like to keep these presentations casual, so if you have any questions, certainly feel free to type them into the questions window. We will try to address all questions during the broadcast. There'll also be time at the end where we'll go through any questions. If you have any questions afterwards, or if we don't get to them during the actual broadcast today, we'll certainly email out responses. There will be a brief survey that will come out after this. We're always interested in the feedback of those who come here to hear us. And without further ado, let's get into pH system design. So, at the basic level, pH neutralization or pH system is one of the most important elements for treating wastewater in any industrial laboratory facility. Anytime you have any kind of an aqueous waste stream, whether that's generated in an academic environment, a pharmaceutical, food and beverage facility, industry, aerospace, semiconductor, it needs some level of treatment before it can be discharged to the sanitary sewer. And your pH neutralization is really what accomplishes this. It's in line, in your actual drainage system. It allows you to treat any kind of waste streams coming into it from a pH perspective, as well as a few other aspects such as thermal, as well as thermo and temperature as well. But it is an integral part of meeting compliance for any of a number of different type of facilities. And there are really two primary factors that come up when doing pH system design. The first is flow. Whether you have a pump flow into your system or it's completely based on the gravity drainage of your system, because that helps determine the size of the tanks, size of the plumbing. It helps to some degree also in sizing some of the various componentry such as the metering pumps and other chemical injection which goes into the system. But also as important is the nature of the waste, whether you have a very strong waste stream, you have a fairly weak waste stream, if there are other constituents that come into play, such as alkalinity, high purity water. These all have an impact on the overall system design, which we're going to address as we go through the broadcast. But first, a little bit of fundamental, talking about the pH scale in general. pH scale runs from 0 to 14 for all intents and purposes. And the important thing to note about the pH scale is that it's logarithmic by nature. The further you get away from neutral, which is 7, in the acidic direction, which goes 6 to 0, or in the basic direction, 8 to 14, you're going up by orders of magnitude. So 7 to 8 is 10, then 100, 1,000, 10,000, etc. So if your pH coming into your system is say pH 2 versus pH 4, the pH is considerably stronger in those cases. And this comes up quite a bit. As you can see here, these are just a number of fairly common household things: lemon juice, soap, bleach. And you actually see how strong they are relative to neutral pH. And the average pH discharge limits throughout the country, and there is some variation in this, as it is a function of the local municipality, what they'll accept, whether you're discharging into, and what you're actually discharging into, generally falls somewhere in the 6 to 9 pH range. So technically pouring your orange juice down the drain actually puts you out of compliance, as far as an actual waste handling is concerned. Throughout the history, pH neutralization systems have been around for about 50 years at this point or so. And, by and large, kind of going back in the day, they used to be considered very passive systems. And I'm sure any of you are familiar with pH systems a little bit, are aware of the old limestone chip tank designs. These have been largely phased out, where basically you were using a medium of limestone where waste would come into the tank, you would settle for some amount of time, and you dissolve the limestone to neutralize the waste. The problem with any kind of a passive system is one, it only treats in one direction. It only treats acidic waste, and obviously there are a number of different constituents out there, which are obviously very basic in nature, cleaning chemicals and the like. That would be completely unfazed by going through a limestone chip system. Beyond that, they're just not very strong. You're talking about a very weak acid source in limestone. I'm sorry, a very weak basic source in limestone. So you can only really treat down to about the pH 4 range with those. Active systems, which are much more common today, which is what this presentation is going to focus on, can treat in both directions, and with the right sizing, they can treat over the entire pH range, whether you're dealing with pH 0 basically to 14 at that point. There are three primary types of pH neutralization systems that are available. The first is the flow-through style system seen here on the left. This is probably 90% of pH systems that are out there, where your waste comes in, whether by flow or by pump, into a treatment tank or series of tanks, is treated, and then is allowed to discharge essentially in a steady state as waste comes in. And this allows you a very high amount of throughput through your system, and also some variance, due to the fact that pH neutralization systems very often do see some fluctuations as far as waste is concerned, between periods of higher flow and then periods of low to no flow coming into your system. The second style system is a batch treatment system, and these are less common, but they do have a number of different benefits. A batch system, waste is transferred into your system. It's held for a predetermined amount of time until the waste is neutralized, while the influent coming into your system is shut off. And then once the waste is neutral, it's allowed to be discharged from the tank. The benefit of a batch system is you basically have no chance of being out of compliance, as you can hold the waste for as long as you like. This is also a good piece of technology to utilize when you have pHs in the more extreme range, say down around 1 or up above say 13 to 13 and a half. The downside of a batch treatment system is very low throughput. Between the fill time, treatment time, verification time, and then pump down time, it can take you almost an hour to treat an entire batch system. As a result, very often you end up, needing to use very large amounts of equalization tanks, or it's just not a feasible feasible design to utilize when you have very high flow coming out of your system. To largely kind of bring both of these different characteristics of flow through and batch together, people have developed a hybrid batch style system. In a hybrid style system, the system operates as a continuous flow through system 95% of the time, and when necessary, it'll go into a batch mode for a short period of time to treat a stronger waste stream coming into it. This is either done by having some built-in freeboard in the neutralization system itself, or diverting back to an out-of-spec tank or an equalization tank located supporting the system. Hybrid flow-through batch systems are, by and large, the most common system utilized in industry because they allow you to treat the largest flow rates as well as the largest variation in waste coming into the system. Regardless if it's a flow through a batch or a hybrid style system, there are numerous similar components which are utilized as part of a pH neutralization system. Treatment tanks, the agitation involved, chemical injection, controlled instrumentation. And you can see here a couple of different examples of really what a pH system looks like. Down here on the right, you have kind of a 4-stage system. That's not very common, obviously. That's more of a result of area going into these things. It is worth noting that pH neutralization systems in general can get pretty big, and that largely has to do with the treatment tanks which are involved in them. So all pH neutralization tanks operate what's referred to as a CSTR, continuously stirred tank reactors. And what that means from chemical engineering is within your tank, as waste is coming in, waste is leaving, and your reagents are coming into your system, you're essentially ending up with like an ideal solution based on the agitation going on in your system. As a result, In the actual pH tank, you aren't so much treating a flow rate, you're actually treating the volume of the tank in that steady state configuration. And you accomplish this through three primary things. Residence time being most important. And residence time for a pH neutralization tank tends to be somewhere between 15 to 30 minutes, again, depending upon the nature of the waste, and then the rate of mixing that's going on in your system. Obviously, we're dealing with acids, bases, and other aqueous chemicals here, so material compatibility is also important. And by and large, most pH neutralization systems are polypropylene or some kind of thermoplastic material. Occasionally, you'll see fiberglass for high temperature and sometimes stainless steel, but 95% of pH neutralization systems are going to be polypropylene by nature. Talking about the mixing here for a second, you can kind of see a cutaway here on the right of a pH neutralization tank, and then the actual inside of a pH neutralization tank here on the left. The rate of mixing is very important in a pH neutralization system. As waste comes in, it's directed down a downpipe, which you can see here on the right, going down to the bottom of the tank, and then right into the mixer backwash. And this allows what's referred to as, this avoids what's referred to as short circuiting of the tank, whereby the waste could come in and basically go straight across without actually entering into that well-mixed solution. The reagent chemicals are also injected right into that mixer backwash as the waste comes in through the downpipe. Now, as a general rule of thumb, the pumping rate of mixing of a pH neutralization tank is approximately 1.5 times the tank volume. There's a little bit more that goes into that, but essentially what you're saying is if you have a 1,000-gallon treatment tank, you need to have 1,500 gallons per minute of mixing to achieve that ideal solution, which is why very often recirculation pumps are not utilized solely for mixing in a pH system, because it just simply will not achieve that level that you typically want to see for a pH neutralization tank. That being said, recirculation pumps do have their benefits in these systems. We'll talk about that a little bit later in the broadcast. But that has more to do with the reagent injection, allowing that to actually be pressurized into the actual pH neutralization mixing, as opposed to directly being involved as a primary agitation source. In addition to the treatment tank and agitation, obviously, since we're treating chemistries, we need to be putting in our reagent chemicals. And by and large, this is accomplished through some type of a metering pump or peristaltic control pump to inject the reagents into our treatment tanks. And the two most commonly utilized reagents are sulfuric acid and sodium hydroxide. Concentrations of these do vary, but the most common being 50% sulfuric and 25% sodium hydroxide. These are kept separately and with the system and are always 110% double contained to comply with OSHA regulations for chemical handling. And these flow, and really the rate of which you're going to be putting these into the system is considerably smaller than what your flow rate is. pH systems can treat 10 gallons, 50 gallons, 500,000 gallons. But because your reagent chemicals are orders of magnitude stronger than your waste stream, your metering pumps are going to be operating at a rate proportional to that. So even though you may have something like 100 gallons a minute of pH 2 to 3 waste, you may only be injecting like 5 gallons per hour of your chemistry coming into your system, just based on that logarithmic nature of pH. And this is accomplished through the proportional control, which is the primary control mechanism utilized in pH neutralization systems. And what that means is, as the pH system is in operation, as you're actually out here in the more extreme side of the pH curve, pH 0, 1, 2, or pH say 11 to 14, you're quite a bit away from neutral. You're much closer to the strength of your reagents, and you're going to run your pump at a higher dosing rate, whether you have a single stage or you have a two-stage style system. And as you get closer to neutral, you basically scale down this proportional to the pH curve until, as you go from 4 to 5 to 6 to then 7, you're proportionally turning down your metering pump by a factor of, 1,000, 110, etc., to meet that goal. And this is based on the real-time feedback that comes from the pH instrumentation located in your pH system. You can see here just a video on the right. That's what a typical pH probe would look like. It's located in the system. The pH probe is located in each stage of the system, stage 1, if you have a 2-stage system, as well as the effluent to allow you for proper treatment and measuring. And this data is then utilized with the actual injection system to allow you to achieve that proportional control. Speaking of instrumentation for a few minutes, there are some other instruments which are also utilized in pH neutralization systems. pH probes obviously being the most important, but flow is also very commonly involved. Obviously, if you have a pH neutralization system, one of the things that you need to look at is actually proving that your pH neutralization system is actually working properly. As a result of that, at the end of usually at the end of the system, you'll have some form of effluent monitoring. This effluent monitoring typically includes pH as well as flow meters, like the one here shown on the screen, that allow you to, one, track the flow being discharged from your system, as well as allow you to record that flow in comparison to the pH to make sure that your pH system is working within the verification steps that are allowed, by your local municipality. In addition, if you're involved with things like a batch process or more of like a hybrid batch system, will you also use actuated valves as a means to shut off that effluent should you actually go out of compliance, with your actual discharge? A little bit separate from the pH neutralization system, but also oftentimes working in concert with them is equalization tanks. And what an equalization tank is it's a tank located upstream of your pH system that allows you really serves two main purposes. One, allows you to equalize the flow coming into your system. And two, it allows for specific volume transfer should you be involved in more of a batch style system. The first one is really important because as a pH neutralization system, you have to size it for the maximum flow rate coming into your system, not the average or something. Because what ends up happening is it's during that high flow period that you're most likely to go out of compliance in your system. And going out of compliance can result in very heavy fines or shutdown of the facility. So it's always best to kind of build that buffer in after you establish your flow profile and size it for the highest, the maximum flow rate coming into your system. The problem is that maximum flow rate might be a very short-lived occurrence. I'm working on a project right now with a client where they're dumping roughly, 3,000 gallons in roughly like 10 minutes into their system, like a 500 gallons a minute. You don't want to size your entire system for that 500 GPM. Obviously, that makes the system very large. You have very large treatment tanks at that point. It's going to lead to stagnation, at other points in the system, as well as increased cost and footprints. This is where an equalization tank makes sense. You transfer that larger volume into an EQ tank, and then you transfer to your system, if it's flow or hybrid style system, at that more continuous flow rate, as opposed to your batch style system where you would then, as opposed to oversizing your system. In a batch situation, you absolutely need an EQ tank because now you're using that as your holding volume. So then when you shut down your effluent, you can transfer that specific volume. So it operates in a very similar capacity between continuous flow and batch systems, but with a batch style system, your EQ tank is essentially becoming that reservoir. You can have those different surges in flow come into it at that point. At this point, we're going to put up a quick poll question. If anybody has any interest in kind of reviewing it, it just kind of goes through a few different things that we've just kind of talked about here in the beginning of the presentation, and we'll talk about it here in about 10 or 15 seconds. All right. And, as we kind of go into, and really this poll kind of highlights sort of where we're going into with the presentation at this point, because it addresses obviously, what is the basis for sizing, from a flow standpoint for sizing a pH neutralization system. And for those of you who reviewed, the answer is obviously the maximum flow rate. And that kind of segues here into what we're talking about, which is the second part, which is, in addition to just looking at the maximum flow rate coming into our system, what other aspect comes into sizing, doing pH system design? That's really the nature of the waste. Flow rate can be a little bit easier to determine. You know what's actually feeding your system, whether it's going to be lab sinks or processes or, what have you, transfer stations. When you're talking about the nature of the waste, it's a little bit harder to kind of determine, okay, I have this entire facility, what is the pH going to be like at my actual pH neutralization system? So that gets to become a little bit more of a tricky point, but it's an equally as important point when talking about when doing a pH system design. So kind of like to do is just kind of a few things you want to look at. One, what type of space are we dealing with? Is it a biology facility, pharmaceutical, chemistry, clean room, animals, manufacturing, food and beverage? There are certain similarities in those, which can often point you to a specific, type of chemistries you'll see. For example, pharmaceuticals and food and beverage, cleaning chemicals become very pertinent in those systems. Um, clean rooms, generally speaking, or semiconductors going to be very, generally going to see things like aqua regia or other acid-based chemistries coming into your system. This can kind of at least sort of point you in the right direction as to what kind of expected waste you're going to see into your system. And the other big one to talk about, obviously, is the presence of high purity water. And I specifically mentioned high purity water because it can become, a fairly big influence in the pH neutralization system. A lot of different facilities will use some form of treated water, whether that's ultra high purity water, USP water, Wi-Fi water, water for injection. And the processes by which you will make that water essentially strips out of the water itself to make it to its purity level. It removes all the alkalinity from the water. And the alkalinity is a measure of the buffering capability or the ability to neutralize acids and bases in a solution. And what ends up happening very often is you'll use this water in the processes, and then you send it down the drain with the balance of the chemistries, and now you essentially end up with a pH neutralization system full of high purity water and some chemicals involved. And the problem is without the natural buffering that you typically see in just basic city water, as you try to neutralize this wastewater, you end up with a lot of fluctuation. So you basically what happens is your reagent chemicals will respond faster than they should within your pH neutralization system. So here you can see kind of looking over time, if you have basically you know, a lot of high purity water in your system, as you begin to do your chemical treatment, you're going to start to see this kind of normal curve, is what you want to see, and it's going to overreact. It's going to do it again and again and again, essentially running down your treatment process considerably longer and using more chemistry than it should be. What you really want to see is what you have here on the right, where you have a nice linear curve, essentially, of pH treatments that's proportional to your reagent injection. To achieve this, what you often need to use in your system is some form of a buffering agent. The most common is bicarbonate, which can be injected alongside your pH neutralization chemistries. And this will allow you to basically add back in that alkalinity, which needs to be utilized in your pH neutralization process. To highlight this, I kind of wanted to take a look at, this is some actual real-time pH data that's utilized on a project. I just kind of want to use this sort of highlight a few different examples here about alkalinity and kind of the nature of the waste. So what we're looking at here on this graph is, here on the right, this is pH. Down here is the amount of reagent volume needed based on the volume of the waste. So what you're looking at here, this kind of like light purple line here, this is what you would typically want to see for standard pH neutralization. As I'm adding my reagent, I have a very linear curve down to 7, and then it kind of continues down. If you keep, this is actually titration data, so it's overextended past the neutral mark in this case. That's kind of your perfect scenario here. Looking at this light blue line here, you can see you have the data points, and then you have this big jump here where you go essentially from 3.5 all the way up to 10. This is the presence of low alkalinity waste in your system. This is what it will end up looking like. You won't get that smooth transition. You're going to see this huge jump when really you should just be going right from like 3.5 to 4 at that point. So this kind of highlights in real data what the impact of alkalinity is in your system. The other one is I wanted to kind of take a look at here is this purple one. As you can see, it's up around the pH of 13.5, and it takes essentially an order of magnitude more chemistry to even get it to start to move down in this case. And this is just, again, showing the logarithmic nature of pH. From way back here, pH 10, I start moving, down around 0.1 reagent volume to waste. Up here, it's a whole order of magnitude plus more to get it going, to really get it moving at that point. And then even here, you see this jump. This wastewater also be considered somewhat high, somewhat low in alkalinity, kind of based on that sort of jumping there as well. So just kind of showing some real-time data here to kind of highlight some of these theories that we're talking about today during the presentation. Moving away a little bit from the nature of the waste, I kind of wanted to highlight a little bit more about the flow profile. Just on the poll question before, you obviously want to size it for the maximum flow rate coming into your system, but it is sometimes not always possible to operate a pH neutralization system solely on gravity. And this comes up very often when you have a pH neutralization system that's going to be located, say, on grade, or your piping has to be sloped underground. And you don't necessarily want to locate your pH system in the ground or in a pit because of the various complexities that are involved in it. People do need to look at utilizing like a lift station. Lift station is a little bit different than an EQ tank, because in an EQ tank you have a tank which you're holding waste for, basically buffering the volume coming into it. In a lift station tank, I'm basically just using this to basically compensate when gravity is not my friend. And like I said before, very often this is the case when you have subground drainage, or you're doing more of like a renovation project and you need to tie this into a new pH neutralization system. So real quickly here about lift stations, just for a few minutes. Lift stations come in two primary styles. There are simplex and then there were duplex style lift stations. Simplex lift stations are often utilized in very simple processes. You have a single pump where you don't have to worry about necessarily the redundancy aspect of the system. If you have, say, a couple of sinks, for example. Duplex style lift stations tend to be utilized more when you're talking about entire lab floor or entire building, where they're going to have that built-in redundancy. Because obviously the worst case scenario is, if your pumps fail, then you have more of a flooding issue in those cases. So how do you develop a flow profile? Developing a flow profile or pH system, if you're talking about things like lab sinks or cup sinks, fume hoods, you can generally assign some value to those, a gallon per minute, half gallon a minute, etc. And then you treat other processes, cage washers, kettles, CIP dumps. Those all need to be taken into account for what their actual discharge flow rates are. Then you need to apply a diversity factor to this. And the diversity factor depends on the type of industry you're in, the frequency of operation. If it's something like academia, for example, your diversity is very low, 20%. More industrial scale could be more like 30%, or whatever your fixed schedule is if it's more of an industrial facility for those different dumps. And then you have to combine them to look at whether it's a gravity flow or if it's a pumped flow application. In a pump flow application, you have to always assume if it's a lift station 100% of the flow rate. That's how lift stations have to be sized. So to kind of run through a quick example here, if I had 80 lab sinks, 5 glass washers, 10 autoclaves, and fixed counts that need to be pumped are 20 sinks and 2 glass washers. I calculate a flow rate of 1 GPM times 20 lap sinks, 20 GPM, 2 cage washers of 16 GPM. I have total pump flow rate of 36 gallons per minute. So lift station sizing is a little bit different. Those tend to run a residency time of about 3 minutes, and you always have to pump them down. So you're generally applying a 10% oversizing to your lift station. So you're looking at about 40 gallons per minute of actual calculatable flow from your flow rate from your lift station. When talking about gravity, this is where you really want to apply that diversity factor. So now I have, say, 60 sinks by gravity, so 60 GPM, but at 20% diversity, you're only going to really see like 12 gallons per minute as kind of a worst case flow rate. Glass washers, 2, and then obviously autoclaves, you end up with a total flow rate of only 38 gallons per minute based on the diversity factor of the gravity drainage aspect of your system. When doing your pH system design, you basically add these two together, 40 GPM plus 38, 78 gallons per minute. Next is looking at the nature of the waste that's involved. And it's best to kind of put an idea of where your pH range is going to fall, barring any outside, strong dumps, for example, or strong outlier waste streams. In this case here, we'll assume pH 3 to 11. This is what we kind of consider standard waste. Standard pH neutralization tends to be somewhere 2 to 13, 2 to 12 range, 3 to 11. This is where majority of basic wastewater will fall, barring the addition of some kind of specific chemistry. Getting to 13 plus or getting below 2 to 1 in that case isn't very common for most pH systems. They can certainly be designed to handle that. This is where majority of waste streams are going to fall, is somewhere in this range, just based on the dilution factor, the chemistries involved, kind of more or less standard waste. And then any high purity water also present in the system. So in this case here, 20-minute residence time, 78 GPM, 1,568 gallons total volume for residency time, and we end up with 2 800-gallon treatment tanks. Sometimes neutralization tanks can be both single and two-stage. There is a benefit to going two-stage in a pH system. The benefit of going two-stage is you essentially have 2 different treatment tanks in series. So you have basically 2 different CSTR reactors, which allows you for more efficiency of control in your pH treatment system. Very common when you have higher flow systems or when you end up with a very strong waste stream coming into your system. We have just at the photo here on the right. These are your reagent tanks, 110% contained. Your reagent metering pumps, both acid and caustic to both tanks. Then you have your effluent monitoring here for these types of systems. Looking at this schematically, systems can get fairly large, as I mentioned earlier, because they are dictated based on the size of the treatment tank, which you can see here on the left. Down here you have your reagents, then over here you have your buffer injection system. P&ID wise, here on the right, 2 treatment tanks, effluent monitoring, reagent injection control, and this would be a lift station here feeding that over here on the right, the extreme right. Bird process equipment has developed a number of basically standard style systems to apply some of these different technologies and sizings that we've talked about. Here on the right, you can see really the smaller package we have, what's referred to as our Phx pH neutralization system. And the Phx neutralization system runs really kind of on the lower side of the flow rates from here down around 7 to 10 gallons a minute, up to about 33 gallons a minute. And these are used very often in small lab expansions. They don't come with a lot of bells and whistles, but they basically come as a prepackaged module. And they're very, very simple to operate. Their power consumption is low. They can run on a 110 volt outlet, basically 12 amp design. And they're very small in footprint. The smallest one here is 2 by 4 foot 1 by 5'9". And, if you're looking at something, for example, this is more like an academic environment, for example, you can basically correlate PHXs to basically the number of sinks that you're going to try to treat in those cases. less than 20 sinks, 90 to 110. Once you get above that, you tend to go into a little bit more of a different style design at this point. Looking at the PHX here, in the front you have your control console. Here you have your reagent metering pumps. This front panel here has your double container reagent tanks, and then here in the back as well, you have your agitation and actual treatment tank. These are sized very similarly. In this case here, just as an example, 75 lab sinks, 30% diversity, 22.5 GPM. Looking at the pH range, 3 to 11. You end up with about 337 gallons, which runs up to about a PHX 400. And schematically, these operate very similar to single-stage pH neutralization systems. Your reagent injection with level sensors, the effluent, agitation, and then your pH probe. Describing the PHX module, I kind of mentioned in the photo earlier, this is your front console here, which is also here. This is where your controls and reagents are. This back section here, as you can see on the left, this is actually your treatment tank, agitation, manuals, and your inlet piping coming down. Cross-sectional view, this is the inlet with the down pipe, reagent injection, metering pump, and then agitation as well. Moving into the more industrial side of things, brew process has developed what's referred to as our assured compliance system. And the assured compliance system is really a true hybrid style design, and these really designed a true industrial, pharmaceutical, semiconductor, larger scale manufacturing. And these scale in size as a single kind of skidded module from 0 to 300 gallons per minute, but as multiple stage modules up to about 1,200 to 1,300 gallons per minute. And these incorporate a number of additional features that we've kind of highlighted a little bit throughout the presentation that allow for treatment of more extreme waste. These can handle waste streams really in that 1 to 14 range. And they can operate that way because they do have in some form an integral batch treatment capacity as well. They utilize things like recirculation pumps to do carrier fluid injection of the reagents. They have more advanced control systems, and they have a number of different options that go along with them. They involve wet tap and self-cleaning pH probes as well, and they can also be built in 2 stages. This is actually one of the 2-stage designs here as well for those types of systems for, again, more extreme waste considerations. Some of the options involved with these include single and 2-stage, as I just discussed, additional diversion equalization tanks, temperature monitoring, redundant pH probes, temperature control, PLC-based bulk reagent transfer, really a number of different features here as well. And the standard for these run in the 50 GPM to 100 to 150 gallons per minute. You can see here this information is all available on the website as well for those who are interested. These range obviously a little bit bigger than the PHX, but again, they're designed for that more integral volume there. And looking at the design, in these cases, you have your treatment tank, as you see here on the right. This is the effluent, where you have that additional freeboard in your system. Looking here on the left, you have your recirculation pump as well as the effluent monitoring and the reagent tanks. It's the front view here as well. PID-wise is probably where it's best to sort of describe these a little bit. You have your treatment tank here. This is where you have what's referred to as kind of the double effluent on these systems, where this is your normal operational level, where the waste will come out. And then up here, this is where you have your additional freeboard. If the waste in your neutralization tank is out of spec, this valve here will close, and then you have this additional freeboard. As an option for some larger systems, you can also have a diversion valve here, which actually brings back to an equalization tank or lift station to really make the system go into a full recirculation mode. In this case, the reagents are not dripped into the tank, but are actually put into a recirculation loop, which you see here, which basically educts it back into the mixer backwash. And this allows for really a faster reagent mixing, which really allows the ACS unit to do a more efficient treatment, because now you're essentially using the wastewater as a carrier medium, and you're reducting it back into the mixer backwash there for a much faster reagent injection. There are a number of these which are also smaller, which are becoming more popular in the market. These are the ACS-10 and ACS-25, again, used for like smaller industrial applications where you see the same benefits of the ACS-style hybrid configuration, but also at that lower flow rate. We've talked a lot today about some of the different theories that have been involved, a couple of different standard pH systems. There's a lot of different customization that goes into these types of systems as well. You can see here on the upper right-hand corner, this is a fiberglass treatment system. This is for high temperature waste, as an example, as a two-stage style system. Down here in the lower corner, this is more just a reagent-based system for more of like if you have an outside tank that you want to inject into. This is often utilized as well. Sometimes people do have that where they'll have like an outflow condition and they'll reuse an existing tank. That's where these type of systems come into play. And these systems can also be hazardous. This example here is a batch treatment system, which is actually rated for Class 1 Div 2 operation. This was for a fertilizer-style facility as well. So there's a number of different ways to kind of customize these systems to bring them into specific client needs. So while you have a lot of standards, we have a lot of sizing, these systems can also be very much customizable to meet the specific requirements of each end user. In addition to just skid-mounted designs, what we're seeing more and more in pH neutralization system, this is very true in the industrial side, people actually put these in to containerize systems. So the benefit of kind of containerizing a system is, instead of having to bring in a skidded system into your industrial facility or into your mechanical or into your educational space, this allows you to basically have a pre-built pH neutralization system, which can be built into basically an outdoor modular facility, which can then be brought to the facility, pre-tested and pre-assembled. There's really all you have to do is basically tie in the final influent and outfluent. You don't actually have to do major construction. You don't have to knock down walls, worry about access. All you basically do is just bring power and bring plumbing to this type of a system, and you can have basically a full treatment system or really any type of system located in a fully modular, environmentally safe enclosure. And you can see here in the video here a couple of examples for one that shipped down to Texas just this past year, just as an example, kind of highlighting more and more what we're seeing, particularly in the pharmaceutical industry, is becoming more and more common. Obviously, not allowing for downtime, the ability to really build, fully turnkey and fully modular systems like this. So, you have more. This is kind of where I see a lot of things kind of going in the future, just as kind of more of an add-on to just kind of your basic pH neutralization system. There's a couple other instructional videos on our website that kind of go through, kind of the basic operation of these systems. Really looking at kind of, this is one of our PHX modules here, and I just kind of wanted to show really quickly. Really the inside of these things, kind of looking, that's kind of what it looks like in the inside of a pH neutralization tank when it's in operation. That's that agitation. It's not actually as high as you think it is. You're kind of looking inside what really goes on inside an actual pH neutralization system, from the metering, the agitation, those are the metering pumps there in the corner. You have your reagent injections there in the back. That's really the heart of really what we've been talking about today, is really understanding how to size that, what the nature of that waste is. And that's really the trick to doing primary pH neutralization design. And then lastly here, I just kind of wanted to show, obviously, as I mentioned, these can get quite a bit bigger. In this case here, this is another pH neutralization as more of a two-stage system. which is designed for 400 to 500 gallons per minute. And, the system technology stays largely the same. You have your agitation, you have your treatment tanks, you have your pH probes, effluent monitoring controls in these types of cases. But really, the system basically just scales to match that. So, really, you can build a pH system to treat any flow rate or any waste. It's just a matter of understanding that principle up front, and then allowing it to scale to be able to actually treat that. So here you can kind of see just a few examples here of one of the larger kind of systems that typically, and this system also is going to be located outside. And again, not all systems go in containers, like as I mentioned earlier, go inside the actual building. Systems like this are more designed to be located, sometimes outside. They can also be winterized to some degree and also made chemically resistant in those cases. So just kind of want to highlight this here and show this is like the equalization tank transfer pumps in these cases. There's a number of different ways, kind of highlighting some of the different technology that goes into these systems. Real quickly, before I get to some of the questions here, I just kind of want to highlight. I want to thank everyone for coming on today. And we have a number of additional webinars coming up here: pump lift stations in April, chemical feed in June, high purity water systems in September, and then custom engineered systems in November. So certainly, I think those registrations are open if anybody is interested in those. And again, I want to thank everybody before I get to some of the questions that we have. So, our first question: what is the process for filling reagents in a self-contained system? So obviously, when you're dealing with reagent chemicals, there's a number of different ways that people handle reagent transfer and reagent handling within the system. So you can do reagents in a number of different ways. You can have onboard reagent tanks, or you can have totes in those cases. They kind of both have their pros and cons. If you have onboard reagent tanks, generally the safest way to do it is to utilize some kind of a drum pump or other pumping technology. If you're going to basically be filling it from a tote that's adjacent to it, but do bear in mind that you do have some type of technology. You do have some type of risk of chemical handling with those types of systems. The downside of utilizing a tote is, even if you bring a tote or a drum in and you bring it into your system, you still have the metering pump, you still have the suction lines. You have to pull those out, put them into a new drum. You're still handling you still have a risk of handling the chemical in those cases. If you have bulk storage and you can run a more permanent line into a reagent system, that's probably the safest way to do, but it's obviously not always a feasible option. Our next question: we have a preferred type of peristaltic pump, diaphragm versus peristaltic? By and large, I'd say I've generally seen electronic diaphragm metering pumps utilized for pH neutralization systems. I have seen peristaltic used sometimes, but a lot of the metering pumps have a little bit more control that can be utilized with some of the systems. But again, it kind of does depend somewhat on preference in those cases. Peristaltic I like a lot when dealing with off-gassing chemicals, like if you have to put hypochlorite into your system, say for some form of biologics treatment, that can be very useful. But like by and large, I would say electronic diaphragm pumps would probably be the most commonly utilized in the system. Are there cleaning slash maintenance of the pH probes, I think is the question. So pH probes can come in a lot of different styles. So there actually are probes which are self-cleaning in those cases. And by and large, how a self-cleaning probe operates is it's going to have a small nozzle on there, which will basically either pass air or will pass water over the pH probe. Because over time, if you do have any solids or biologics in your system, you do run the risk of actually getting some clumping in the system, so that you would you may want, the probe can get blind or start giving false readings. Biologics in particular can actually cause the pH probe to read acidic, because the actual metabolic process of the biologics in the waste can actually cause the probe to read that way. So it is fairly important to have that kind of cleaning involved in the system. What is the requirement for the pump used in the pH system? So pumps serve a lot of different purposes in a pH neutralization system. If it's a transfer pump, it's obviously going to be sized for the flow rate coming into your system. If it's a metering pump, it needs to be sized based on the chemical you're utilizing to the assumed waste of your system to allow for that proper proportional control. And if it's in a recirculation mode, that if it's actually a recirculation pump, that pump's flow rate is not that relevant. And because really what you're trying to accomplish there is, what you're really trying to accomplish there is you're trying to basically allow your reagents to be ducted into your waste stream under controlled conditions. So most injection is done by drip. So what happens is the metering pump is in operation and it basically drips into the waste stream, based on the readings. And then how the recirc pump is basically I'm just basically drawing off of the tank and I'm recirculating it into an eductor, which then magnifies that flow rate. But really what it's doing is basically just carrying my reagents under pressure and then educting it into the mixer backwash. So there isn't a lot of there isn't necessarily a critical amount of sizing that's required for that recirculation pump in that situation. If the waste stream is primarily neutral but contained a lot of Wi-Fi water, is buffering necessary? Yes and no. So the one thing about if your waste stream is primarily high purity water, probably the most important thing is to utilize a high purity water rated pH probe, especially if your waste doesn't really require much treatment. High purity water can actually leach the ions out of a lot of different pH probes, and that can actually lead to false readings in the system. So the first thing to probably check if you have a lot of Wi-Fi water is to actually put in a high purity rated pH probe within your actual system. And if you do have to do treatment, it would probably still be advisable to put the buffering in. But if you're just doing monitoring in that case, I'd say that that's probably the most important thing with the system. One more question. Can CO2 gas be utilized as a pH neutralization reagent? Yes, it can. So in some instances, people will utilize carbon dioxide gas as a reagent chemical. And how you really do that's a little bit different than treating, which is an acid or a base system. And in those cases, what happens is you have a diffuser located in the bottom of your tank, and as the system is in operation, you actually basically modulate CO2 gas, will then pass up through your mixer backwash, and then obviously fade into the atmosphere above the tank. It's a little bit different sizing for those types of systems. As you have to utilize both the tank height as well as some different porosity of CO2 gas in those cases for treatment. But you certainly can use CO2 gas as a fairly common thing that goes on in the food and beverage industry. What is the impact of discharging high temperature waste into a pH neutralization system? So by and large, it's kind of a twofold question. If you have, generally speaking, you cannot discharge waste which is above either 104 degrees Fahrenheit or 140 degrees Fahrenheit. So you do need to do some kind of a thermal control before you actually hit that point, particularly in the United States. pH neutralization systems, the actual treatment tanks themselves and some of their componentry can be rated to a higher temperature, but generally they run to about 180 to 185. So if you do have a high temperature stream, and I see that quite a bit, where you will see people will dump like direct steam condensate and things like that, it's generally advisable rather than trying to build the pH system to be very high temperature to actually just do the quenching upstream of it, whether that's by a heat exchanger, which is probably the most common, or some form of other thermal control in the system. That will really allow you to then one, solve the actual discharge limit issue, which is the pH, which is the temperature control, and then two, also allow you to keep the pH system, without having to go into the added expense of adding all of that temperature into your system. So the question is there a limit for flow rate or pressure for the system that required to not exceed for calculations of pH? So when you're talking about a pH systems are generally atmospheric, so pressure isn't so much of a concern, unless you're obviously going to be pumping into it at some extremely high pressure. Unless barring some unusual designs, pressure is not a huge concern in the pH neutralization system. And really, so long as you know what the flow rate is coming into your system, you can size it appropriately. So there isn't per se a limit in the system to that. Again, if it's going to be more of an intermittent high-level flow, you might want to look at putting in an equalization tank in those cases. Are there adverse effects of having oil in wastewater? Yes, there is. Unfortunately, things like oil, and that depends on the type of oil, obviously that we're talking about here. Oil is not very good in a waste stream. Really twofold. One, you may not be able to discharge it, period, the oil, because it might be a violation of the permit. Because again, we're talking about things that are going to be mostly in the aqueous stream, going to sanitary sewers. So you probably may need to separate it out anyways from a permit standpoint. But in addition to that, pH, different types of oil can also have a coating impact on the instrumentation involved in the system, which could be detrimental. So it's probably advisable to actually remove the oil upstream if you can into like an oil water separator, just because of the coating nature. Now, trace amounts, it happens all the time. People put that in, but if you are seeing a fairly large amount of oil, I would remove it before bringing it into the system. All right, everyone. I think that brings us to just about 2 o'clock here. Again, we'll hang out for a few more seconds, but if anyone has any more additional questions, you can feel free to post them here or send us an email, and we'll be happy to get back to you. Again, thank you very much for everyone for coming on today. Again, look forward to seeing everyone in April, hopefully for the next webinar. Thanks a lot.